Welcome to the heart of a gold mega factory, where the Earth's raw treasures are transformed into one of humanity's most coveted metals. Gold's symbol of wealth, beauty, and power has captivated civilizations for millennia. But how does this precious metal go from buried rock to gleaming bars, jewelry, or high-tech components? Today, we're taking you on an extraordinary journey through a state-of-the-art gold mega factory where cutting-edge technology, human ingenuity, and relentless precision create billions of dollars worth of gold every year. From the depths of the earth to the global market, this is the story of gold production on an epic scale. Let's begin where it all starts, deep in the ground.
Once the ore arrives at the mega factory, the transformation begins in earnest. The first stop is the crushing and grinding circuit, a noisy, dusty world of brute force and precision engineering. Primary crushers, towering machines with steel jaws, break the ore into smaller chunks, roughly the size of gravel. These chunks move via conveyor belts to secondary crushers, which reduce them further. Finally, ball mills, giant rotating drums filled with steel balls, grind the ore into a fine powder, almost like sand. Water is added, turning the powder into a slurry, a muddy mixture that's easier to process. This step is crucial. It liberates gold particles trapped within the rock, making them accessible for extraction. The crushing circuit operates around the clock, handling thousands of tons of ore daily. Automation plays a big role. Sensors monitor particle size, and AI-driven systems adjust the machinery to maximize efficiency. Workers, clad in safety gear, oversee the process, ensuring no blockages or breakdowns halt the flow. The energy demand is immense. A single mega factory might consume as much power as a small city. Yet, this relentless grinding is just the beginning, preparing the ore for the intricate chemistry that follows. With the ore now a fine slurry, the next phase is separation and concentration, isolating gold from the gangue. This is where science takes center stage. Gravity separation is often the first step. Gold is denser than most surrounding rock, so devices like shaking tables or jigs vibrate the slurry, causing heavier gold particles to settle while lighter materials are washed away. It's a simple but effective method, often recovering larger gold flecks early in the process. For finer particles, flotation is the go-to technique. The slurry is mixed with water and chemicals that make gold-bearing minerals hydrophobic. They repel water. Air is pumped into the mixture, creating bubbles that these minerals cling to, floating to the surface as a frothy concentrate. This froth is skimmed off, leaving behind waste rock. The result: a concentrate where gold content jumps from less than 1% to over 20%. In advanced mega factories, AI optimizes chemical doses and bubble size, boosting recovery rates to 90% or higher. It's a delicate balance. Too much chemical can contaminate the concentrate, too little can miss gold particles. Skilled technicians monitor every variable, ensuring the process hums along efficiently. The concentrated ore now enters the leaching and extraction phase, where chemistry dissolves the gold into a liquid form. The most common method is cyanidation, used by mega factories worldwide for its reliability. The concentrate is mixed with a dilute cyanide solution in enormous tanks, some holding millions of liters. Oxygen is bubbled through to accelerate the reaction as cyanide binds to gold particles, dissolving them into a solution. Safety is paramount. Cyanide is highly toxic, so modern factories use closed systems and strict protocols to protect workers and the environment. For lower-grade ores, heap leaching is an alternative. Ore is piled into massive heaps, often covering acres, and sprayed with cyanide solution. The liquid slowly percolates through, collecting gold as it drains. This method is slower but cost-effective for marginal deposits. The output of both processes is a gold-rich liquid called pregnant solution. Some mega factories experiment with greener alternatives like thiourea or thiosulfate to reduce environmental impact, but cyanide remains the industry standard due to its efficiency. Gold, the metal of kings, the foundation of economies, and a symbol of eternal value. Hidden deep within the earth, it takes a colossal effort to transform raw rock into the shimmering bars and intricate jewelry that define wealth. Welcome to the Gold Mega Factory, a marvel of modern engineering where science, technology, and human determination converge to produce billions of dollars worth of gold annually. In this journey, we'll uncover every step of the process, from the depths of the mine to the global market. Buckle up for an inside look at one of humanity's most ambitious industrial feats. The story of gold begins long before the first shovel hits the ground. It starts with exploration, a high-stakes treasure hunt driven by geologists who blend science with intuition. Using satellite imagery, they scan vast landscapes for telltale signs of gold geological formations like quartz veins or ancient river beds. Ground-penetrating radar and magnetic surveys reveal hidden structures beneath the surface. Core samples, drilled from depths of up to 3 kilometers, are analyzed for gold content, often measured in parts per billion. In a megafactory's supply chain, this phase is critical as it determines whether a deposit is worth mining. A single exploration project can cost millions and take years, but finding a viable deposit like those in South Africa's Witwatersrand Basin or Nevada's Carlin Trend can yield billions in gold. Once a deposit is confirmed, the mining operation springs into action. There are two primary methods, each tailored to the gold's location. Open pit mining targets surface deposits, creating massive craters that can span miles. Giant excavators, capable of lifting 50 tons in a single scoop, remove overburden layers of soil and rock covering the ore. In contrast, underground mining tackles deeper veins. Miners drill tunnels, some stretching for kilometers below the surface, using diamond-tipped drills and controlled explosives to blast gold-bearing rock. Ventilation systems pump fresh air to workers, while robotic drones map tunnels in real time, ensuring safety and precision. The ore, a mix of rock and trace gold, is loaded onto trucks that can carry 150 tons per trip. A megafactory might process ore from multiple mines, handling 50,000 tons daily. To produce 1 ounce of gold, 31.1 grams requires up to 30 tons of ore, highlighting the sheer scale of this endeavor. The ore arrives at the megafactory's receiving bay, a chaotic symphony of raw material and machinery. Here begins the crushing and grinding circuit where brute force meets precision engineering. Primary crushers, often gyratory models with 60-inch openings, break the ore into chunks the size of soccer balls. These machines can process 5,000 tons per hour, their steel jaws driven by motors consuming megawatts of power. The crushed ore travels via conveyor belts, some stretching over a kilometer, to secondary crushers, typically cone crushers, which reduce it to gravel-sized pieces. Next, ball mills take over. These are colossal rotating drums up to 8 meters in diameter, filled with steel balls that pulverize the ore into a fine powder, finer than beach sand. Water is added, creating a slurry with a consistency like wet cement. This grinding liberates gold particles, often microscopic, from the surrounding rock. The process is energy-intensive. A single mill might use enough electricity to power 10,000 homes. Automation is key. Sensors measure particle size, and AI algorithms adjust mill speed to optimize output. Workers, trained in mechanical engineering, monitor the system, ready to intervene if a blockage threatens production. Dust control systems, using water sprays and filters, keep the air breathable, while noise-canceling headsets protect workers from the deafening roar. This relentless operation runs 24/7, transforming raw ore into a slurry ready for gold extraction. The concentrated ore now enters the leaching and extraction phase, where chemistry dissolves gold into a liquid form. Cyanidation, used by 80% of global gold production, is the dominant method. In massive tanks, some holding 10 million liters, the concentrate is mixed with a dilute sodium cyanide solution, 0.05% concentration. Oxygen is bubbled through, accelerating the reaction as cyanide binds to gold, forming a soluble complex. The process, known as carbon-in-leach also involves activated carbon granules that absorb the dissolved gold, streamlining the next step. Safety is critical. Cyanide is highly toxic, so factories use sealed systems, automated monitoring, and emergency neutralizers like sodium hypochlorite. Workers undergo rigorous training, and air quality sensors ensure no leaks endanger the team. For lower-grade ores, heap leaching offers a cost-effective alternative. Ore is stacked in heaps, sometimes 100 meters high, and sprayed with cyanide solution over weeks or months. The liquid percolates through, collecting gold in a pregnant solution that drains into collection ponds. Liners prevent contamination of groundwater, and modern factories recycle 70% of the water used. Some mega factories explore greener alternatives like thiosulfate leaching, which avoids cyanide but is less efficient. The pregnant solution, whether from tanks or heaps, is the key to the next phase, carrying gold in a form ready for capture. The pregnant solution now undergoes adsorption and elution to isolate the gold. In carbon-in-pulp CIP or CIL tanks, activated carbon acts like a sponge, binding gold while leaving impurities behind. The loaded carbon is then stripped in elution tanks where high-pressure solutions up to 150 degrees Celsius and 5 atmospheres release the gold into a concentrated liquid. Electrowinning follows. Electric current plates gold onto steel cathodes, forming a sludge that's 70 to 80% pure. This sludge is dried, then smelted in furnaces at 200 degrees Celsius, producing door bars rough gold that's 90% pure but mixed with silver and copper. For 99.99% purity, refining is the final hurdle. Electrolysis using the Wohl process passes current through a gold chloride solution, depositing pure gold onto cathodes. Alternatively, the Miller process uses chlorine gas to remove impurities, achieving 99.5% purity in less time. The molten gold is poured into molds, cooling into bars or ingots stamped with weight and purity. For jewelry, it's alloyed with metals like zinc or nickel to improve durability, then cast into rings, necklaces, or watch components. Quality control is rigorous. Spectrometers verify purity, and artisans inspect jewelry for flaws. The finished products, whether bullion for banks or earrings for boutiques, are shipped worldwide, fueling economies and dreams. Gold, humanity's ultimate symbol of wealth, beauty, and power. For thousands of years, it has shaped empires, driven economies, and inspired dreams. But transforming raw earth into gleaming gold bars or intricate jewelry is no small feat. It requires a gold mega factory, a technological marvel where science, engineering, and human ingenuity converge to produce billions of dollars worth of gold annually. Today, we'll take you deep into this process, from the geologist's hunt for hidden deposits to the final pour of molten gold. This is the story of a gold mega factory where every step is a testament to precision and scale. Let's begin. The journey to gold starts not with machines, but with science. Exploration is the first chapter, a meticulous quest led by geologists who are equal parts scientist and explorer. Their mission: find gold deposits buried in the Earth's crust, often in quantities so small they're measured in parts per billion. Using satellite imagery, they scan vast regions for geological clues: quartz veins, fault lines, or ancient riverbeds that hint at gold. Ground-penetrating radar and electromagnetic surveys map subsurface structures, while core samples, drilled from depths of up to 3 kilometers, are analyzed for gold content using X-ray fluorescence and fire assay techniques. These samples, often just a few centimeters wide, can determine whether a site holds billions in potential. Exploration is a high-stakes gamble, costing $10 to $100 million per project and taking 5 to 10 years. Only 1% of explored sites become viable mines. In a megafactory's supply chain, this phase is critical as it dictates the quality and quantity of ore available. Geologists like Dr. Sarah Patel, who works at a leading gold producer, describe the thrill. Finding a deposit is like solving a puzzle the Earth has hidden for millions of years. Every core sample is a clue. Successful discoveries, like South Africa's Witwatersrand Basin source of 40% of all gold ever mined or Nevada's Carlin Trend, can fuel a mega factory for decades. Environmental regulations now require community consultations and impact assessments, ensuring mining aligns with local ecosystems and indigenous rights. Separation and concentration isolate gold from worthless gangue. Gravity separation exploits gold's density 19.32 grams per cubic centimeter versus rock's 2.7 grams per cubic centimeter. Nelson concentrators, spinning at 2000 rpm, recover coarse gold particles, capturing 60 to 70% of free gold. Shaking tables, vibrating at 300 cycles per minute, use water to wash away lighter materials, leaving gold behind. For finer particles, flotation is critical. In 50,000-liter tanks, reagents like potassium amyl xanthate make sulfide minerals hydrophobic. Air pumps create bubbles 1–2 millimeters wide that gold particles cling to, forming a froth skimmed by automated paddles. The concentrate, now 25% gold, is filtered and dried. AI optimizes flotation, adjusting reagent doses to within 0.01% for maximum recovery up to 95% in top factories. Chemists like Dr. Raj Patel monitor pH levels, typically 10 to 11, to prevent reagent breakdown. Waste tailings, 90% of the original ore, are pumped to engineered dams with geomembrane liners to prevent leaks. Modern factories neutralize tailings with lime, reducing acidity, and recycle 80% of processed water. Tailings are our biggest challenge, says environmental engineer Lisa Wong. We're testing bioremediation to make them safer. The concentrated ore, now gold-rich, is ready for chemical extraction. Leaching dissolves gold into a liquid form, a process dominated by cyanidation. In carbon-in-leach sill tanks, the concentrate is mixed with a 0.05% sodium cyanide solution. Oxygen, injected at 10 parts per million, accelerates the reaction. For O plus 8 NaCN plus O plus to HCO gives for NaAuCN A plus for NaO. Activated carbon granules, added directly, adsorb the gold complex. Each tank, holding 12 million liters, processes 1,000 tons of slurry daily. Automated sensors monitor cyanide levels, ensuring safety as even 0.1% concentrations are lethal. Workers undergo 40 hours of hazmat training, and emergency systems can neutralize cyanide in seconds. Heap leaching, for low-grade or 0.5 grams per ton, involves stacking ore in 100-meter high piles across 50 hectares. Sprinklers apply cyanide solution, which percolates for 60 to 90 days, collecting gold in a pregnant solution. Impermeable liners and monitoring wells protect groundwater. Some factories, like those in Nevada, recover 70% of gold via heaps, recycling 75% of water. Green alternatives like thiosulfate leaching reduce toxicity but cost 20% more. The pregnant solution, gold-laden, flows to the next phase, carrying the factory closer to its treasure. The pregnant solution enters adsorption and elution. In carbon-in-pulp CIP tanks, activated carbon captures 99% of dissolved gold. The loaded carbon is stripped in elution columns at 140 degrees Celsius and for atmospheres, using a caustic soda solution to release gold. Electrowinning plates gold onto steel cathodes via 400 amps of current, producing a 70% pure sludge. Smelting in induction furnaces melts this into door bars, 90% gold with silver impurities. Refining via the Wool process uses electrolysis in a gold chloride bath, achieving 99.99% purity. The Miller process, faster, injects chlorine gas to remove base metals, reaching 99.5%. Molten gold is poured into 400-ounce bars for bullion or alloyed with copper for rose gold or palladium for white gold for jewelry. Casting machines produce blanks for rings, while artisans hand-polish designs. Spectrometers verify purity, and X-ray scanners detect flaws. In 2024, global gold demand reached 4,900 tons, 45% for jewelry, 30% for investment, 10% for tech. A single mega factory produces 50 tons annually, worth $4 billion. Every bar tells a story, says refiner James O'Coy. From miners to markets, it's human effort in solid form.